Okay, so we've been talking about directional derivatives, and mostly just to understand and see visually how they work, we've been using the idea of the slope of a surface in three-dimensional space. Um, that kind of gives you the good idea of what a directional derivative can mean in terms of uh, elevations and stuff like that. But how does this apply to anything, in real life here that we are interested in? And so I like this example from our book, number 31, particularly at this time when we're, all stuck inside our houses with COVID-19 out there. And so this is the infectious disease model that I introduced earlier on a previous video. R naught, if you recall, is a measure of how many new infections that an infected person causes when they're in a population that's completely susceptible to getting the disease. And it's a measure of the number of days a person is in that population while they're contagious and the vaccination rate of your population. And R naught is a very important number in epidemiology. If you've been following the news lately, you've probably heard that number talked about. Okay, so for example, let's say our R naught value, if D is 2, so if a contagious person is in the population for an average of 2 days, and if our vaccination rate is 10%. And if you plug that in here, you're going to get an R naught value of exactly 3. So what that says, at a vaccination rate of 10%, when an infected person is in the population for 2 days, that person will infect an average of 3 people. Think about that. One person infects 3 people. Each of those people would infect 3 other people. You can imagine the kind of exponential growth that would occur. An R naught value of 3 is very high. That's very troubling. Okay. So what's something public health officials can do? Let's say in our scenario that they're considering a reallocation of resources that will have the effect of increasing our vaccination rate. That's a good thing, right? That would reduce R naught, but it comes at a cost of increasing D, the number of days an infected person is in the population. Of course, that would have a bad effect. That would increase R naught, right? How could that happen? If you tell everybody there's a vaccine and everybody runs to the hospital, you got a big crowd of people, including infected people, that may have a cost, right? That might increase D, right? That's not a good thing. So, they have to think about these things carefully. So the net effect, though, in this scenario, it kind of depends, right? How is the effect of increasing the vaccination rate better? Is that a better effect than the negative effect of increasing D, right? It depends on how much these changes of V and D affect R naught. So let's get more specific now. Let's say, and this is the book's example, let's say that it's known or it's thought that our reallocation is going to have the result of increasing D twice as much as V. And so the question is this a beneficial plan? So if you think about it, this is a directional derivative question, because what we're really trying to find out is what is the rate of change of R naught? How is that going to change? And we could think of this as a vector, right? Increasing D twice as much as V, you can think of that as a vector. And so what we want to know is what's the rate of change if we're at our point 2, 0.1, and we move in the direction of 2, 0.1. I'm sorry, 2, 1. Okay, so this is a directional derivative. And we know how to calculate this now. First step, we're going to want to normalize this vector, turn it into a unit vector by dividing by its magnitude, which is root 5. So we get 2 over root 5, 1 over root 5. Then we're going to take our partial derivatives to make our gradient vector. Now the partial of R naught with respect to D, I'm treating V as a constant. and 5 is a constant as well, and this is multiplied by our d variables, so that just gets to stay there, and we're going to need a quotient rule to take the derivative. And we reduce that down, I get 1 over 1 plus d squared. If we plug in 2 for d and 0.1 for v, we get a value of 0.5, 1/2. Okay, taking the derivative with respect to v, now I'm going to treat d as a constant, and so this time that d over 1 plus d gets to stay there, the 5 gets to stay there, and the derivative of 1 minus v is -1. If I evaluate that at my point, I get -10/3. So then I can compute my rate of change of my function in the direction of u. It's my gradient vector dotted with u, and when you do the math, we get -7 over 3√5. Now remember, in this case, the object is to decrease r0, right? We want that to be a low number. So the fact that we got a negative result, that's a good thing, right? This would be a beneficial move. Now, if that's beneficial, then the next question I would imagine public health officials might be thinking is, well, is there some way we could improve this and decrease r0 even better, even faster than this, right? Is there some way to reallocate our resources? So the object here, in terms of ratios in d to changes in v, what is the best possible strategy for reallocating our resources? Okay, so the goal here is to decrease r0 in the most rapid way. And we talked about earlier that one of the properties of the gradient is the gradient vector itself points in the direction of maximum increase in the function. So if you wanted to decrease your function most rapidly, it makes sense you would move in the opposite direction of your gradient. So in this case, we want the negative direction of our gradient, which we had worked out. And that gives us -1/2 and +10/3. So, okay, in theory now, right, if we could decrease d by 1/2 while increasing v by 10/3, or in that ratio, right, the ratio of those two, that's what would give us the maximum benefit at our current values of d being 2 and v being 0.1. Right, that's going to decrease r0 in the most efficient way. Anyhow, I kind of like that problem, especially because it's very current with the situation we are with our world right now. So, and it's a good example of seeing directional derivatives in the real world. Okay.